Okay, good afternoon, everyone. In the beginning of the class, let us look at the new announcements. Okay, the first new announcement is April 25th, 2022 class videos uploaded. Hello everyone. I have uploaded the class videos of April 25th, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. Okay, the next new announcement is the slides of Chapter 3 has been updated. Version 2022-0427. Hello everyone. I have uploaded the latest version of the slides of Chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website. Multiple input, multiple output techniques for wireless communications. Course content, slides, chapter 3, slides 2022, 0427.pptx. Best regards, Wei Zhen. Okay, the next new announcement is the handout of Chapter 3 has been updated. Version 2022-0427. Hello everyone, I have uploaded the latest version of the handout of Chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website. Multiple input, multiple output techniques for wireless communications. Course content, handouts, Chapter 3, handout 2022-0427.pdf. Best regards, Wei Zhen. Okay, next let us look at the progress of the last class. Okay, in the last class we have taught to Chapter 3, slides, page 66.1 unfinished. Okay, please open your slides of Chapter 3 and turn to page 66. Okay. Excuse me. As we have mentioned, for the normalization used in equation 3.21. Okay, let us see equation 3.21. Okay, in equation 3.21, okay, the received signal vector is given by r, which is equal to the square root of rho. Okay, whereas before rho denotes the total power received at each receive antenna from all the transmit antennas divided by the thermal noise power at each receiver. And H is the channel matrix. V, okay, what is V? Okay, let us go back to the previous slides. Okay, the matrix V is a unitary matrix, okay, such that H is equal to U D V Hermitian. Okay, this is the singular decomposition of H. Okay, let us go back to here, and S tilde. Okay, what is S tilde? Okay, let us go to this page. Okay, assume that at some instant the transmitter has R symbols, where R is the channel rank, are symbols to transmit, which we denote by S tilde, is defined as S tilde 1 to S tilde R transpose. And plus Z. Okay, what is Z? Okay, let us go to the first Z. Okay, let us see. Okay, Z is the NR by 1 noise signal vector. Okay, let us go back to page 66. Okay, the square of the Frobenius norm of H is equal to NT times NR. Okay, where NT is the number of transmit antennas and NR is the number of receive antennas, and sigma square is equal to 1. Okay, what is sigma square? Okay, let us go to the first sigma square. Okay, so sigma square is defined as the expectation of the square of the absolute value of Zi, and it is equal to 1. Okay, this the equation number should be aligned right. Okay, so it should be this, like this. Okay. Okay, then let us go back to page 66. Okay, and sigma square is equal to 1 are implied. It can be shown see problem 3.4. Okay, let us go to problem 3.4. Okay, problem 3.4, prove equation 3.29. Okay, let us see equation 3.29. Oh, I think it is a bug of PowerPoint. Okay, after I save the file and open it again, the position of the equation numbers will be changed. Okay, this is equation 3.29. Okay. So that under such assumptions, it follows that summation I is equal to 1 to R, Pi is equal to 1. Okay, what is Pi? Let us go back to the previous page. Pi is defined as the expectation of the square of the absolute value of S tilde I, where I is equal to 1 to R. Okay, which functions as our constraint in this problem. Solving for the optimum set of Pi is a standard constraint optimization problem, which can be solved using the Lagrange multiplier technique from the calculus of variations. Okay, I think you have learned what is the Lagrange multiplier when you take the course calculus. Okay. However, if you did not learn it, okay, that is okay. We will review this technique in the following pages. The resulting algorithm that implements this solution is called the water filling algorithm. Okay, with a constraint optimization problem, there is a function that needs to be optimized that depends on a set of variables and a constraint imposed on those variables. In our application, the function that we seek to optimize is the eigenbeamforming capacity in equation 3.27. Okay, let us go to equation 3.27. Okay, In equation 3.27, we can see that CEIG, okay, which is the capacity with eigenbeamforming, is equal to summation I is equal to 1 to R, okay, where R is the channel rank, and log 2 of 1 plus rho, where rho is the SNR at the ends at the receiver, and times the expectation of the square of the absolute value of S tilde I. Okay, what is S tilde I? Let us review it. Okay, here, okay, assume that at some instant the transmitter has R symbols to transmit, which we denote by S tilde is defined as S tilde 1 to S tilde R transpose. Okay, so S tilde I is the I's symbols to transmit. Okay, let us go back to page 67. Oh, sorry, not 67. Okay, 68. Oh, sorry, not 68. Go to equation 3.27. And times lambda I, okay, where lambda I is the I's largest eigenvalue of the matrix H times H Hermitian. Okay, let us go back to page 68, which is a function of Pi, and the constraint is given by equation 3.29. Okay, let us go to equation 3.29. Okay, in equation 3.29, we can see that summation I is equal to 1 to R, okay, where R is the channel rank. Pi is equal to 1, okay, where Pi is defined as this, okay, the expectation of the square of the absolute value of S tilde I, and S tilde I is the ith symbol to be transmitted. Okay, the first step is to write down an expression called the functional, which is an equation that results from writing down the function that is to be optimized and then adding to it a scaled version of the constraint. In our case, the functional has the following form, okay, J of P1, P2 to PR is equal to summation I is equal to 1 to RR, okay, log 2 of 1 plus rho Pi lambda I plus beta times summation I is equal to 1 to R Pi. Okay, where beta is a constant called the Lagrange multiplier. Next, we take the partial derivative of J with respect to the variables that we are attempting to optimize, that is Pi, and set them equal to 0, which results in the following. Okay, so partial J over partial Pi is equal to 0, and it is equal to the partial derivative of J with respect to Pi. Okay, so it is equal to this term. Okay, and be taken the partial derivative with respect to Pi. Okay, because it is a log 2 function. So after the derivative, it is equal to 1 plus rho times Pi times lambda I times natural log 2. Okay, because the log function, the base of the log function is 2. Okay, then according to the chain rule, we must multiply it by the d rho I by d pi. Okay, where rho I is equal to rho pi lambda I and plus beta. Okay, because this term, if we take the partial derivative with respect to pi, then we will get beta. Okay, and after evaluating this derivative, we will get rho lambda I, okay, over 1 plus rho pi lambda I times natural log 2 plus beta, where I is equal to 1 to r. Okay, solving this equation for pi yields, PIOPT is equal to minus beta times natural log 2, 1 over beta times natural log 2 minus 1 over rho lambda I plus. Okay, we will explain what is the plus mean later. And it is equal to mu minus 1 over rho times lambda I plus, where I is equal to 1 to r, where mu is defined as minus 1 over beta times natural log 2, and x plus is defined as x excuse me. Okay, if x is greater than or equal to 0, and x plus is defined as 0 if x is smaller than 0. Okay, let us see how to derive equation 3.32. Okay, please look at the blackboard. Okay, because I do not have a blackboard, let me use the Microsoft Word instead. Okay, let me see. It is chapter 3 and page 72, problem 1. Derive equation 3.32. Okay, so problem 1 should be boldface. Okay, solution. Okay, solution should be boldface. Okay. From equation 3.31, we know that. Okay, let us go to equation 3.21. Okay, this equation. So we need to copy this. Okay, and paste here. Oops. Okay, so 0 is equal to rho lambda I over 1 plus rho pi lambda I times natural log 2 plus beta, where I is equal to 1 to r. Okay, so we call this equation 1. Okay, next, then we will solve pi. Okay, so first, we will get a fraction here. Input a fraction here. Okay, so first rho times lambda I and over 1 plus rho pi lambda I. Okay, let us type first. Okay, it is equal to minus beta and times natural log 2. Okay, like this. Okay, and the next, okay, it implies that okay, it implies that so we can take the reciprocal of the both sides of this equation. Okay, then let me input a fraction. Okay, then rho lambda I will go to the denominator, and 1 plus rho pi lambda I will go to the numerator, and it is equal to minus. Okay, so a fraction again. So the numerator is 1, and the denominator is beta times natural log 2. Okay, like this. Okay, so next, okay, it will implies that 1 plus rho pi lambda I is equal to this times rho lambda I. Okay, so it is equal to minus rho lambda I over beta natural log 2. Okay, so it implies that we move the term 1 on the right hand side of the equation. Okay, so rho pi lambda I is equal to this term, minus rho lambda I over beta natural log 2 minus 1. And the next, it implies that pi we divide the equation by rho lambda I. So this term becomes minus 1 over beta natural log 2 and minus a fraction 1 over rho lambda I, like this. Where I is equal to 1 to r. So let me align this equation. Oh, no, not this. Like this. Okay, so good. This is equation 2. So next, let us continue. Because pi is defined as let us see defined here is defined as the expectation here of a curly brackets, a pair of curly brackets. Then the this one and the absolute value like this. Okay, it is 25 minutes. Let us take a break.